All right, so previously we obtained the transfer function, right, earlier on in the module here. Then we converted that transfer function into the rectangular form of a complex number, right, with a real and an imaginary part. And then from there, we found the magnitude of that complex number. And that's what we got here. This is in terms of frequency f. This is in terms of frequency omega, okay? And so what we're going to do now is we're going to find the angle or the phase of that same complex number here. So let's go ahead and grab this and bring it over with us to the next slide. All right, so let's do that. So let's paste. So this is my imaginary number. And I need to find the angle, which if you recall, the angle of a complex number is basically equal to the tan inverse of the imaginary part divided by the real part, which in this case, I'm not going to write it as phi, actually. I'll write it as the angle of V out over Vs. And so in the numerator, I'm going to have the negative of the imaginary part, which is going to be omega RC divided by 1 plus omega RC squared. And then that whole thing is going to be divided by the real part, which is going to be 1 divided by 1 plus omega RC squared. So right off the bat, hopefully you realize the two denominators just cancel each other out, and I get that this is just the tan inverse of negative omega RC over 1, which is equal to just the tan inverse of negative omega RC, which there is a trig identity that says that the tan inverse of negative something is equal to negative the tan inverse of something, right? That's a trig identity. So let me actually write that in a different color so that we have it on the page. Just throw it in orange or something. Just put it up here. Okay. And so then we can rewrite this as the angle of V out over Vs is equal to negative tan inverse of omega RC. And I can go ahead and box that, and that is the phase of my transfer function. Or I could write it again. I can substitute omega equals 2 pi f, and I could rewrite it as V out over Vs is equal to the negative tan inverse of 2 pi f RC. All right, so we have our angle here, and we have our magnitude here. Oops. Let me go ahead and grab these. They're very important. So we've got phase here, and we've got magnitude here. And so now from here, this is where we can generate our plots, because again, recall what we just did. We just took our transfer function. Here's our transfer function, the ratio of the output voltage V out to the input voltage Vs, and we rewrote it in terms of a complex number in a rectangular form, which has a real part and an imaginary part, correct? Once we do that, we know that we can take from the rectangular part into a phasor, which has a magnitude and an angle, phase, right? Well, if we can do that, that means that we can determine a function, right, which we just did. We determined a function for V out over Vs, right, the magnitude of V out over Vs as a function of frequency f, or it can be written as a function of omega, whichever you prefer. Typically, we're going to write it in terms of f because it's more common to work with hertz than it is to work with radians per second or angular frequency. But we basically found the magnitude of that complex number here, which represents our voltage conversion ratio, or our voltage gain, or our transfer function for this particular circuit. We have our magnitude. We went and got our phase, which is here, which is also a function of frequency, right? We plug in a different value of frequency, we're going to get a different value of phase. And that's kind of what I was trying to show here, where I show that for different values of frequency, we get different values of phase. For different values of frequency here, we get different values of magnitude. And that corresponds to that signal, which is the output of our network or our circuit or whatever system it is that we're analyzing. Okay, in this case, it happens to be an RC circuit that we're analyzing. Okay, so we have our magnitude, we have our phase, and so now the time has come where we need to generate these plots, right? For real. I just sketched these roughly. These are not real magnitude and phase plots. I had just thrown something together to show you that this is basically what we're going for when we do frequency response. We now have these functions, right? We have the magnitude function as a function of frequency. We have the phase function also as a function of frequency. So what we can do, and what we're going to do in the next video, I'll go ahead and end this video. We're basically going to generate these two plots where we're going to plot frequency on the x-axis, and on one of these plots we're going to plot the magnitude, so we can see what happens to the magnitude of our transfer function for all values of frequency. And then we're going to do the same for the angle, and those two plots are what we're after when we do frequency response. Okay, so this is going to be our magnitude plot, this is going to be our phase plot, and then that will give us the frequency response of the RC circuit that we see here. Okay, so I'm going to go ahead and end this video here, and in the next video we'll go ahead and create those plots. We'll go ahead and sketch them.